In this deep dive, we'll uncover exactly what happens under the hood when you hit deploy on a smart contract. Think of it like sending a new digital vending machine into the blockchain network. By the end, you'll understand how your Solidity code becomes live on Ethereum's blockchain. Let's get started. First, what is a smart contract? Simply, a smart contract is a program that runs on the Ethereum blockchain containing code, its functions, and data, its state, at a unique address. It's like a digital vending machine. You send in cryptocurrency and select an option, and the contract's code automatically dispenses the correct output, like a snack. As Nick Szabo's metaphor suggests, with the right inputs, a certain output is guaranteed, all hard-coded in software. The Ethereum Virtual Machine, EVM, is the computer that runs these contracts. It's the computation engine built into every Ethereum node. You can think of the EVM like a huge decentralized calculator or CPU. It takes bytecode, compiled contract code, executes it step by step, and updates the global Ethereum state. The EVM is Turing complete, can do arbitrary calculations, but it's limited by gas, which measures computational effort. A smart contract is an on-chain program, not controlled by any one user, and the EVM is the decentralized computer that executes it. Next, let's walk through the workflow of deploying a contract using popular developer tools. Two common tools are Remix, a browser IDE, and Hardhat, a local development framework. The basic steps are similar. Write your Solidity code, create a new .sol file, and write your contract. In Remix, you just click New File and start coding. Compile the contract. The Solidity compiler turns your human-readable code into EVM bytecode and an ABI, application binary interface. For example, while using Hardhat runtime environment running npx hardhat compile, generates an artifacts folder containing the contract's ABI and compiled bytecode. The compiled bytecode, including constructor and init code, is packaged into a special Ethereum transaction. In Remix, clicking deploy creates this transaction. In Hardhat, you might write a deploy file script that calls getContractFactory and deploy function, which under the hood creates and sends the transaction. This sends the deployment transaction into Ethereum's mempool, pending pool, so miners or validators can include it in a block. In Remix VM, a simulated blockchain, this happens instantly, but on a real network you'd wait for confirmations. For example, Hardhat helps you compile, deploy, and test your contracts. It even spins up a local Ethereum node for testing. When you compile in Hardhat, it writes out the ABI and bytecode. Deploying then just sends that bytecode to the chain. Remix makes it easy. Select the Remix VM environment and deploy. In a live environment, you'd connect a wallet as an injected provider and approve the transaction. Compiling and deploying generates bytecode, the raw instructions the EVM will execute. Importantly, there are two stages of code here. When you compile, the bytecode includes initialization init code and the final runtime code. The init code contains your constructor and setup logic. It runs once during deployment. At the end of that execution, it returns the actual runtime code, which becomes the contract's permanent code on-chain. In other words, deploying a contract is a bit like running a mini program. First, the constructor init code executes, sets up storage and variables, and then it outputs the contract's machine code. The EVM then stores only the returned runtime code as the contract's code. The constructor and any constructor arguments are not part of the final code on-chain. Now this is a crucial point. All constructor logic runs only at deployment. After that, only the runtime code remains in the blockchain state. You can verify this by looking at EVM opcodes. The early instructions handle construction, and then there's a return of the runtime portion. Now let's look at how the transaction is formed and broadcast. A contract deployment transaction is a special kind of transaction from an externally owned account, your wallet, that has no recipient address. Instead, it carries the compiled init bytecode in its data field. When you deploy in Remix or Hardhat, that transaction is crafted and sent out. Once created, the transaction enters the Ethereum network's transaction pool, mempool, miners or validators after Ethereum switch to proof of stake, then pick it up, include it in a new block, and begin executing it. The EVM processes the init bytecode as part of that block. If you're using Remix's local VM, this whole process happens immediately. On real testnets or mainnet, you'd confirm the MetaMask prompt and then wait a few seconds for mining. When your deploy transaction is mined, the EVM executes it. This both creates a new contract account and runs the init code. The network then records the resulting runtime code at the new contract address. As the Remix docs note, the transaction is created which deploys the instance of the contract. On a real network, you'd approve and wait for it to be mined. What do miners or validators actually do? They act like the shipping company and quality control for your contract. In proof of stake Ethereum, validators bundle pending transactions into blocks. During block execution, each node's EVM runs the new contract's init code exactly as part of the normal transaction execution process. The EVM operates on a stack machine model and reads opcodes from your bytecode. For example, when your constructor code runs, each instruction, like push1, msstore, etc., executes in order. The EVM's job is to faithfully execute these instructions, update the state, and enforce gas limits. Every step costs a bit of gas, so complex constructors use more gas. Because this happens on every validating node, it ensures decentralization. Every node ends up storing the same new contract code and state. As QuickNode explains, the EVM participates in block creation and transaction execution, using opcodes to update the ledger state. In summary, miners validators include your deploy TX in a block, run the EVM on it, and record the new contract. We've mentioned gas a few times, now let's explain it. Gas is the fuel that pays for computation on Ethereum. Every instruction in the EVM costs a certain amount of gas, and every transaction specifies a gas limit and pays for the gas used. When you deploy a contract, you pay for all the steps of the constructor init code. Gas is measured in Wei or Gwei, small units of ether. For example, assume your deployment uses 3 million gas, and the gas price is 20 Gwei. We calculate it as 3 million multiplied by 20 Gwei. Since 1 Gwei equals 10 to the power of minus 9 ether, the total cost comes out to 0.06 ether. Gas prices can fluctuate with network demand. The key point is that more complex contracts cost more gas. Always check gas estimates. Both Remix and Hardhat can simulate the deployment and show estimated gas. If you run out of gas, the deployment reverts and you lose the gas fees. That's why setting a sufficient gas limit and understanding gas usage is crucial. And the EVM won't even start to create the contract if you don't send enough gas with your transaction. Once the deployment transaction is successful, a new contract address is generated. How is this address determined? By default, Ethereum uses the create scheme. The address depends on the deployer's address and their nonce, transaction counts. This means that if you know an account's address and nonce, you can deterministically calculate where its next contract will be deployed. In simple terms, it's kekak256 RLP sender and nonce. This means each time you send a contract create transaction, you get a unique address, assuming your nonce increases. However, there's also create2, a newer opcode. Create2 lets you pre-compute the contract's address before deployment. It uses the deployer address, a user-supplied salt, and the contract's bytecode hash. The contract address is calculated using this formula: kekak256 of 0xFF plus deployer address plus salt plus the hash of the bytecode. Then we take the last 20 bytes as the contract address. Let's break down it. 0xFF, a fixed constant used to avoid collisions with normal create addresses. Deployer, the wallet or contract address that is deploying the contract. Salt, a user-defined value that lets you control and predict the address. kekak256 bytecode, the hash of the contract's init bytecode, takes the last 20 bytes to form the final Ethereum address. In practice, create2 is used for deterministic deployments, so different networks or different times yield the same address, given the same inputs. Most simple deployments use the regular method create. Just remember, no matter how the address is generated, the new contract lives at that address on-chain after deployment. Where does the deployed contract actually live on the blockchain? In Ethereum, every contract has an account in the global state. Each account stores a code hash and some storage. According to the Ethereum spec, a classy code hash is the hash of the EVM code of this account. The actual bytecode is stored in a database. Merkle Patricia try by this hash. In simpler terms, the blockchain state keeps a pointer code hash to your code. All full nodes have a copy of the world state, so everyone can retrieve the code. When you deploy, the new contract's runtime bytecode is written into the state. The actual code bytes are stored in the state trie, not directly in blocks, but because the state root is part of each block, everyone knows exactly what code is at that address. In short, it is on-chain. The network records your contract's address, balance, initially 0 ETH unless you sent value, and storage. The code itself is effectively on-chain as part of the state trie and immutable, cannot be changed after creation. Not everything about your contract lives on-chain. Let's clarify what's on the blockchain versus what's off-chain. On-chain data includes all blocks transactions with their hashes, contract code as discussed, and the state, storage variables, balances. Every byte of your contract's deployed code, every function call, every event emitted, it all is in the blockchain history or state. Off-chain are tools and metadata. For example, Etherscan is an external service off-chain that indexes and displays on-chain data. If you search your contract address on Etherscan, you'll see a user-friendly page. Transaction history, contract ABI, if verified, balances, etc. Etherscan also lets you verify your source code by matching it to the on-chain bytecode. This doesn't change the blockchain, it just provides transparency. In other words, Etherscan reads the chain. It doesn't store anything that isn't already on-chain, except the source code you upload for verification. Similarly, Tenderly, an advanced developer tool, sits off-chain. It watches the blockchain and lets you simulate or debug transactions. It can replay what happened on-chain, but it relies on the actual on-chain data. So think of blockchain as the single source of truth, immutable history, and tools like Etherscan, Tenderly, or even your own local logs as lenses to view and analyze that truth. Up till now, we've talked about what happens during deployment. Now let's talk about how developers actually see and debug all of this in real life. And before anything else, let me introduce a tool that many pro-Ethereum devs quietly rely on. It's Foundry. Foundry is a blazing fast Rust-based Ethereum toolkit built for serious smart contract development. It gives you Forge for compiling, testing, and deploying contracts, and Cast for interacting with the blockchain directly from the terminal. What makes Foundry special? Tests run insanely fast. You get deep stack traces when something breaks, and you can even simulate deployments and transactions locally with full control. Hardhat, a local dev environment, it runs a local Ethereum node so you can deploy with scripts, run tests, and debug. Hardhat even provides detailed error stack traces for Solidity and integrates with tools like Tenderly, Etherscan, the Block Explorer. It's not a deployment tool, but after deploying to a public network, you can search any TX or address. Etherscan shows you the transaction details, gas used, status, and lets you verify source code for public contracts. This is great for transparency and auditing your deployment. Tenderly, an advanced simulation and debugging platform. It offers a transaction debugger to pinpoint exactly where a contract transaction failed, a simulator to test changes, and a gas profiler to optimize usage. As Tenderly advertises, it gives the most detailed stack trace for your contract calls, and you can simulate transactions to test and validate bug fixes before sending them live. With Tenderly, you can catch errors or inefficiencies in your deploy process in a highly visual way. These tools help you see what's happening. Finally, a few common pitfalls to watch out for. Gas estimation errors. Always check that you've set a high enough gas limit. Large contracts or complicated constructors can exceed the default. If you get an out of gas error on deploy, you may need to refactor or provide more gas. Network selection. Double check you're on the right network, mainnet versus a testnet. It's easy to accidentally deploy to the wrong chain or a local network. Nonce mismatch. If using multiple wallets or scripts, keep track of nonces. A wrong nonce can make your TX be ignored or stuck. Unverified code. If you deploy without verifying source, future developers or auditors will struggle to read your code on Etherscan. Take a minute to verify on Etherscan to add transparency. Overly complex constructors. Heavy loops or external calls in the constructor can fail or cost a ton of gas. Keep constructor logic simple. You can always call functions after deployment if needed. Immutable bug. Remember, once deployed, the code is immutable. There's no undo button. Use upgradable patterns or careful testing if you think you might need to patch logic later. As one security blog notes, beginners often underestimate gas costs and write inefficient code, leading to high fees. Use your development tools wisely. Simulate, test thoroughly, and use the Hardhat or Remix debuggers or Tenderly's debugger to find problems before deploying for real. One click, but hundreds of things happen inside the EVM. Under the hood, your code is compiled into bytecode, bundled into a transaction executed by every Ethereum node's EVM, and recorded as an immutable contract on the blockchain. We hope this deep dive has demystified each step from writing Solidity to seeing the contract live on chain. If you like this deep dive, be sure to subscribe for more Ethereum development tutorials. Happy coding and safe deploying.